Okay, we're going to do 2 or 3 example proofs here, and the proofs that I'm going to do with you on videos are going to be similar to the proofs that you're going to do in your homework. So if you get stuck, try to see if you can match up the one in the homework to the one we did in the video. Proofs can be a little bit tricky because there's not a set way of going about them. So what I'm going to try to do is I'm going to try to show you some patterns or some ideas here that you can just kind of apply or copy several times. The more you see proofs and the more proofs that you do, the better you get at trying to figure out what to do. But right when you're starting off, you don't always know the next step to make, and so you just need to gain some experience. So in this case, we got a segment here, and all the proofs we're going to do today have to do with segments. Later we're going to do proofs with angles, and again, the more that we do, the more that it's gonna help. But at first, sometimes this can be tricky. So this is our diagram that we're given, and our information is that we know that t is the midpoint of SU. That's not the only given information we have. We also know that the measure of ST is 7x and the measure of TU is 3x plus 20. And we want to prove this. So this is kind of bridge the gap between the algebraic proofs that we did yesterday and again taking one more step into geometry land. There's still going to be some algebra that happens here for sure, but we're going to start with shapes and kind of move into algebra from there. So we're going to start with our 2 columns, okay? And we have statement on the left and justifications on the right. All right, now again, the first statement in a proof is always the given. So T is midpoint of the segment SU, and that's given. Okay, and then the last statement that we're going to have somewhere down here is x equals 5. We don't know how we're going to get there just yet. We probably are going to have to set some stuff equal to each other, but we can't do that right off the bat because we have to start with this guy right here. What does T being the midpoint of SU really mean? What does midpoint mean? Okay, so when we're doing a proof, the justifications, remember, they have to be some already established piece of information that we have. So what is fair game is postulates, definitions, we have theorems later, we'll have theorems, but we don't have any right now to work with. And we can do constructions that we've already made, and we can use properties of congruence and properties of equality. So that's pretty much the only things that can go over here. In an axiomatic system, if you're trying to prove something, you can't just pull something out of left field and say, well, because I said so. You have to base it on something that you've already established is true. Whether, again, that's a postulate, or a definition, or a theorem, or a property, something like that. Those are the only things that can go over here. Things that we've already know are true, that we've already established are true. So what we have to do is we have to go back to midpoint. If we want to know what the next statement is, we got to think about what does midpoint tell me. So the definition of midpoint, well, it's the middle of a segment. Okay, what else do we know about midpoint? It cuts the segments into 2 congruent pieces, right? If T is the midpoint of SU, then that means that ST is congruent to TU. And that's, again, just by definition of midpoint. So what I can do is I can say these guys are congruent to each other. Okay? So my next statement is that ST is congruent to TU. And how do I know that? What am I calling upon to say I know that this is true, right? We're trying to prove this case to the jury, basically, with deductive reasoning. And the reason what we're going to say is that's just the definition of midpoint. Okay? We know that that's true. The next thing is going to build on here, right? So then we got to talk to ourselves about congruence. Well, what does congruence mean? What does it mean to say that 2 things are congruent? What does that tell us? Well, it means they're the same length. That's the definition of congruence. And so the idea is this length is equal to this length. Now, you heard me just use a word, equal, right? Here, we're talking about congruent. We're talking about shapes being congruent. I just said, well, that means they're equal, right? So I can move into equality by calling upon the definition of congruence. So the next thing I'm going to say here is that ST is equal to TU. Now notice the difference. This is a segment that's congruent to a segment. This is a measurement that's equal to a measurement. All right? Now this is kind of important because at this stage, I can do all kinds of stuff now. I can do substitution, I can do addition, subtraction, division, all that kind of stuff. I can't do that up here. I'm not allowed to add two things to either side or divide both things by a certain side because this is congruent. It's not an equation. This now all of a sudden is an equation. And all that stuff that we did yesterday with equations now is coming back into play. So definition of congruence. I like to say def of Kong because it sounds cool. That's the definition of congruence there. We move from congruence to equality by just saying the definition of congruence means that these two things are equal. That may not seem important, but it's really, really important because, again, now we got 4 more properties that we didn't have before. We have addition, subtraction, multiplication, division, and substitution. All right, the next thing we can do here is we can just do a substitution, right? We can say, well, ST, the measurement, is equal to 7x, so I can do this. TU is equal to 3x plus 20. Right? And what do we do there? That's the substitution property of equality. I'm allowed to substitute something with what it's equal to. And this figure tells me that ST, the measurement, is equal to 7x. So we kind of have to read that, that figure. So this is substitution, prop of equality. Now remember, with substitution, don't just put sub, because there's a subtraction property of equality. Don't just put substitution, because there's not a substitution property of congruence. We have to be specific that we're talking about a property of equality and substitution. Okay, now we're pretty much down to what we were doing yesterday. We're just trying to prove that x equals a number, right? We switched gears from geometry into algebra land, and now we can do all the stuff that we want to do. And what do we want to do here? Well, we probably want to get the x's all together. So we can minus 3x. Again, we don't write that on a proof because this is supposed to be kind of formal, like a formal argument. If we were doing an equation, we would do this, and then I would cross this out and draw a line underneath it. We're not going to do that, but we're going to write the next line. So if I minus 3x here, this is going to cancel. If I minus 3x here, I'm going to have 4x. Right? And what property was that? That was the subtraction property of equality because I subtracted 3x from both sides. So for subtraction, we'll do that. So substitution, subtraction. Okay, subtraction property of equality. Next thing we want to do is get x by itself, so divide both sides by 4. Again, if I was doing an equation, I would do this, but I'm not going to do that. We're just going to go, sorry. We're just going to do it in our heads, kind of. So divide by 4, divide by 4. Okay, and that's the statement that we wanted to prove, right? X is equal to 5. So we're done. But how do we get there? Well, sorry, we're almost done. We got to the last statement. We still got to say why that's the case. And this is the division property of equality. Okay, so now we're done, right? And we proved what we set out to prove. That doesn't seem like too earth-shattering right now. You're like, well, why would you want to prove that? This is just a specific case. That's true, but we're trying to build our intuition about proofs, and we kind of start real slow, real basic, just talking about just basic ideas, generic kind of problems. This will allow us to prove theorems in the future once we get really good at this. But this is how you do a 2-column segment proof. And this guy right here is going to be used a whole lot. Definition of congruence. How many postulates do we have? How many definitions do we have? How many properties do we have? There's a ton. We've defined so many terms out there. We've defined, or we've written a bunch of postulates. There's a ton of postulates in your book. There's Euclid's 5, but then we added more on top of that. But there's a few things that I'll just kind of tell you right now that you're going to use quite a bit. This is going to be huge. You're going to use that all the time, just all the time in proofs in general. But especially on today's proofs, you're going to use the definition of congruence a lot. You're also going to use the definition of midpoint a lot. That's another thing that you're going to use. Not in this theorem, but not in this proof, but in the future proofs that we're going to do. Another one that's really big that you're going to use is the segment addition postulate. And when we're about to use segment addition postulate, I'll refresh you guys on that and what it means. That's going to be a really important one as well. And then the properties of equality that we talked about yesterday. So you're pretty good at subtraction and addition and multiplication and division and substitution. Those are things that you've already used quite a bit. those are going to be there as well. So if you're thinking to yourself, there's so many postulates, there's so many definitions floating around in my head, how am I going to know what to use? I'm going to try to narrow it down for you so you kind of know it's one of a few things. Midpoint, definition of congruence, segment addition postulate are going to be a big deal in this assignment.